So let us take a look at the application side of the crystal field theory. So this is the most important area from coordination compounds we are going to go through. So like predicting the stability, for example, so we'll chalk out the important application part which we'll be going through in this session. So the stability, then the high spin and the low spin complexes, high spin and low spin, outer and inner orbital complex, outer and inner orbital complex, magnetic properties, hybridization and geometry, hybridization and geometry. So these are the areas CFT anyhow we have calculated, and also we have gone through the electronic configuration. Also we will go through once again writing the electronic configuration. And so on and so forth. So many application part of the crystal field theory will be taking care in this session. So we will be focusing on stability of the complex, whether the complex is a high spin complex or the low spin complex. Octahedral, the outer orbital or inner orbital complex will be predicted, and magnetic properties, hybridization, geometry, electronic configuration will also be predicted. So we will go one by one, students. So we will be focusing on the hybridization and geometry at the beginning. So then using that we will be trying to predict the other properties. We will have some of the shortcuts to directly predict the answer from the coordination compounds. Okay. So we will take one by one. For example, I will take octahedral complex to begin with. For instance, I will take COCl6 3 minus, or COCl6 the negative charged complex, right? So K3COCl6 I will take it. So the next one is we will take copper complex, copper hexa aqua copper complex. We will take it as a sulfate hexa aqua copper complex, and we will take some of the strong ligand containing complex also. Fe, for example, CO6, it's a neutral ligand, right? You can keep it as positive charge, Fe plus 2, right? Plus 2 you can take it. So or you can write it as again Cl2, you can write it. So MnCN 6 times sulfate. So these are the complexes, octahedral complex of choice, just for just for the example's sake. So representative example we had taken, and we will try to predict the various properties, like mainly we will focus on the hybridization and geometry. So try understanding here. See, it's all our octahedral complex. If the number of the ligands are 6, then it's an octahedral complex. Obviously it's all our octahedral complex, and hence the hybridization will be 1s orbital and 3p orbital and 2d orbital will be involved in hybridization. Are you getting my points? I will repeat. So hybridization, you will be having 6 hybridized orbital, because it's an octahedral complex. We have 6 coordination bonds, and hence the hybridization will be coming from 1s, 3p and 2d. Altogether you will have a 6 hybridized orbital. It can be, students, 2 ways to look at it. It can be the involvement of d orbital. As far as the involvement of the d orbital is considered, either the inside inner d orbital may be involved, that is inner 3d orbital may be involved in case of the 3d series transition elements. Inner 3d orbital could be involved, or else outer 4d orbital can be involved. I will repeat, either inner d orbital can be involved or outer d orbital can be involved during the hybridization. That is, you have two categories, either d2 sp3 hybridization possible or sp3 d2 hybridization is possible. So both the cases the geometry is the same, that is octahedral geometry, but the hybridization will be different. One is involvement of the inner d orbital, in second case there is an involvement of the outer d orbital. Very clear? So two ways to look at, one is d2 sp3 hybridization, one another option is you have sp3 d2 hybridization. Two options are there. That is, accordingly, if at all there is an involvement of inner d orbital, such kind of complexes we refer it as inner orbital complex. Inner orbital complex. If there is an involvement of outer d orbital, then we will call it as outer orbital complex. Outer orbital complex. Try to understand, two ways to look at, I will repeat. Either the involvement of inner d orbital can take place or the involvement of outer d orbital take place. Accordingly, we can name it as either an inner d orbital or as the outer d orbital, outer orbital complex or inner. One of the question which could be asked. Very clear. So hybridization, you know the geometry and whether it is an inner orbital or outer orbital. Remember students, very simple one. So whenever there is an involvement of the strong ligand, what happens is the energy carried by the strong ligand is very high. So it will make the inner d orbital to pair. It will make the inner d orbital to pair. For example, if you are having 3d orbital, for example, if you are having the 5d orbitals are there, 1, 2, 3, 4, 5 will be there, right? 5d orbital. You have 4 electrons like this, right? If the energy, if it is a strong ligand, energy carried by the strong ligand is very high. So what it does is it will make these 4 electrons to pair, and make it as like this. That means 2 of the orbital will be empty, which can receive the electron from the ligand, which can start receiving the electron from the ligand. A pair of electron from the ligand can be received. That means what is happening, what's basically happening is the inner d orbital will be participating in the hybridization. On the other hand, if it is a weak ligand, what it does is the electrons remains as such. There is no question of the pairing of this electron. So you will be having involvement of the s orbital, p orbital, and outer 4d orbital which is empty will also receive the electron from our ligands. Ligand will give the electron, or the ligand electron will be accommodated in the outer 4d orbital, not in the inner 3d orbital. In the case of 3D series, coordination complexes I am talking about. So that is an important aspect. So, or in other words, if there is a strong ligand complex, so make a note of it, important students. That is, what we mean to say is, if it is a strong ligand, if it is an octahedral complex, I am talking about the octahedral complex. In an octahedral complex, two possibilities are there. One is D2sp3, another one is sp3d2. sp3d2. These two, hybridization will be having the option. D2sp3 will be possible when you are having D2sp3 means it is an inner orbital complex, right? Inner orbital complex. And sp3d2 means it's an outer orbital complex. It's an outer orbital complex. Clear? If it is an inner orbital complex, the inner orbital complex will be formed by strong ligands. Remember, if it is a strong ligand, you can straight away conclude the hybridization is D2sp3 and the complex is inner orbital. Very easily you can predict it. So the outer orbital complex happens when the ligand is weak. So weak ligands, right? So I already said one of the clue I had given is, as far as the strong and weak ligand is considered, if the carbon and the nitrogen is a coordinating atom, it will be considered as a strong ligand. If the oxygen and the halogen atoms are the coordinating atoms, then it will be a weak field ligand. Or in other words, can I say, students, the hybridization in these two octahedral complex, it is octahedral because 6 ligands are there, 6 monodentate ligands are there, 6 coordination bonds are there. Can I say in these two complex, the hybridization is sp3d2? sp3d2 is the hybridization, and this particular complex is an outer orbital complex, very important, outer orbital complex, right? So, and these two complexes which contain strong ligands, the carbonyl and the cyanide, can I call this as an inner orbital complex, or hybridization is d2sp3? d2sp3 is the hybridization involved. Very clear? So I'll repeat again, one of the important aspect which could be asked is whether the given complex is outer orbital or inner orbital. What is the hybridization and the geometry? In the octahedral complex I am talking about. In the octahedral complex, two possibilities, d2sp3 or sp3d2. d2sp3 is possible when you have a strong ligand. Such kind of the system where there is an involvement of the inner d orbital in the hybridization is what is called as inner orbital complex. If there is an involvement of the outer d orbital in the hybridization, then it is called as outer orbital complex. Very clear? So same way you can predict n number of complexes which is given as far as the octahedral complex is considered. This is the one of the general thing. Let us now move on to the next aspect, high spin and the low spin complex. High spin complex, see, generally, in general, what happens is, as we already said, the inner orbital will be getting paired. The electrons which are present in the inner d orbital will be paired, students, when there is a involvement of the strong ligand. When there is an involvement of the weak ligand, the inner d orbital will not, electrons present in the inner d orbital will not be paired. That means there are lots of unpaired electron which will be left out, students, when there is a weak ligand. Or in other words, extending the same idea, can I say high spin complexes are the one in which the weak ligands are involved? You know, this is applicable in most of the cases, although there are exceptions. So high spin complexes are possible when there is an involvement of the weak ligand, and low spin complexes are possible when there is an involvement of the strong ligand. Strong ligand. Clear? So, or in other words, can I say from this inner orbital complex is a, most of the cases they are all low spin complex, and weak field ligand involvement, which is a outer orbital complex, which is a high spin complex. That is, the number of the unpaired electron will be higher in these cases, high spin complex. Clear? High spin complex will be there. I am predicting based on the, mainly based on the ligand, strength of the ligand, so which is applicable most of the cases you can predict it based on the ligand strength.